My name is Amita, and in this video I am going to discuss about another topic of power electronics, that is the class D commutation. Dear friends, I hope you know what is commutation, but if you are not aware, I just want to tell you that it's a process by which we can change the state of a conducting SCR to the blocking mode. It is a process to turn off the SCR. There are two kind of commutation methods are available. One is called as a natural commutation and second one is called as a forced commutation. Natural commutation can only occurs when the connected supply to the silicon control rectifier is of AC type, because AC by nature it passes through zero two times in one complete cycle. So when it completes its positive cycle and when it goes to the negative cycle, in between it passes through zero. So that means at that instant the voltage across the SCR will be zero, and after that it will go to negative cycle. And if the connected load to the SCR is resistive, so at the same time when the voltage passes through zero and later on reverse bias, the current will also be zero. So both conditions of making SCR will be fulfilled. One is it should be reverse bias, another the current flowing through the SCR should be zero. So as the both conditions are fulfilled, so the SCR will be off. This kind of commutation is called as a natural commutation. Why natural? Because we have not used another external circuit. The SCR is commuted because of the connected AC supply. So that's why it is called natural commutation. The second one kind of commutation is called as a forced commutation, when the connected supply to the silicon control rectifier is DC or AC. In case of AC, suppose if you want to make the SCR off during positive half cycle itself, then the natural commutation is not possible. Why? Because the natural commutation of SCR can only happen when the AC passes through zero and goes into the negative cycle. So under the circumstances, if you want to make the SCR off during positive cycle itself, or the connected supply to the SCR is DC, then our dependency is on forced commutation. There are two kind of forced commutations are there. One is called as a voltage commutation and another is called as a current commutation. Let us talk about a voltage commutation. Voltage commutation is as the name indicates, in this kind of commutation, artificially we create a voltage and we apply that voltage across the SCR which is already conducting in the reverse bias condition for a sufficient duration, and then the SCR will be off. That kind of commutation is called as an voltage commutation. So as the SCR is off because of the reverse applied voltage, so its name is voltage commutation. The second is current commutation. In case of current commutation, with the help of some external circuit, we try to flow the current through SCR in an opposite direction, and the time at which the current flowing will be zero through the SCR, the device will be off. That kind of commutation is called as a current commutation. And as in this video, I am going to discuss about in class D commutation. That commutation is a type of voltage commutation. So now let us talk about class D commutation. It is also called as an auxiliary commutation. I will tell you why it is called auxiliary commutation. It is also called as an impulse commutation. The very important thing about it, it is a type of force commutation technique. That means when the connected supply to the SCR is DC, then this technique can be applicable. The second thing is, in a force commutation, it is a voltage commutation technique. As I already mentioned in the introduction that there are two kind of force commutation technique. One is the current commutation and another is the voltage commutation. So it's a type of voltage commutation. L and C are the major elements which we are using for the commutation circuit. What is commutation circuit? It's an external circuit, and with the help of this external circuit, we artificially create the conditions to make the main SCR off. Now, in this video, the topics which I am going to cover, we will see power circuit diagram, we are going to see its operation, and we are going to discuss about its wave. So these three things I am going to discuss in this. Now let us talk about the power circuit diagram. So if you see the power circuit diagram of in class D commutation, that this is the power circuit diagram where supply voltage Vs, this T1, Vs, T1 and load, that makes the main circuit, and this C, TA, L, D, S, RC, all these are the part of a commutation circuit. Means this makes this is the external commutation circuit which develops the favorable conditions to make the main SCR off. T1 is the main SCR which we want to commutate. TA is the auxiliary SCR which is the part of a commutation circuit. C and L are also the commutation circuit part. RC, here you can see this RC we have used to limit the charging current, because what happened before start of commutation process, we initially develop the voltage across capacitor. So what we do, we make this switch close. So when this switch is off under the condition, due to this supply voltage, the current is flowing like this through C, RC and close switch and Vs, and because of that charging current, the capacitor is initially charged by a voltage of Vs with upper plate positive and lower plate negative. So what is the use of this switch S and RC? Is the use of this S and RC is to initially develop the voltage across this capacitor, and that is the condition to start the commutation process. Now let us discuss about its operation. When we talk about its operation, there are few assumptions. One is capacitor C is initially charged by voltage Vs with upper plate positive and lower plate negative with the help of switch S and RC. RC, why we use? RC we use to limit the charging current. The second thing is semiconductor devices are conducting. Whatever the semiconductor devices we have used in this, maybe the main circuit or a commutation circuit, all are the ideal devices, and when they are conducting, they are having zero voltage drop across. Load is highly inductive and carry the continuous load current. So these three are the assumptions for this commutation. Now let us talk about mode 1. Mode 1 may you can see, if you see the power circuit diagram, this T1 is forward biased because of this supply voltage, and at the T is equal to 0 itself we have given the firing pulse to T1. So you can see mode 1 mein T1 is conducting, as due to supply voltage it is forward biased and firing pulse is given to it at T is equal to 0 itself. TA is reverse bias. Why TA is reverse bias? Because when this T1 is short circuit, due to this capacitor voltage, through this T1 will appear to this TA with anode, with cathode positive and anode negative. So that means this capacitor voltage through this T1 short circuit is appearing to TA as a reverse bias. So that's why it is off. Similarly, this capacitor voltage through this T1 short circuit is appearing to diode also. But across diode it is appearing as a forward bias. So diode is forward bias due to the capacitor initial charge voltage, whereas TA is reverse bias. So let me discuss about, because the complete operation of this commutation we can explain with the help of various modes. So this is the first mode, that is called as a mode 1. This is mode 1 which exists between 0 to T1. You can see in mode 1 devices, what are the devices on? Mode 1 mein T1 is on, and you can see T1 is also on and D is also on. So this will be the equivalent circuit. So T1 is acting as a short circuit, D is acting as a short circuit. Now in this case there are two closed paths are there through which a current can flow. One closed path is plus Vs, T1 load and minus Vs. And in this closed path, the current flows, that is called as a load current, which is represented by I0, and its value is Vs by Z. Z is nothing but it's a load impedance. This is ZL is Z. Suppose load impedance we are representing by Z. So this current will be Vs by Z, that is called as a load current. The second path through which a current can flow, that is C, T1, L and D, and then minus plate of C. And in this closed path, the current flows, that is called as a charging current, and this charging current is flowing through a LC circuit. And we know when a DC source is feeding to a LC circuit, this is the magnitude of a current, or the expression of current that we can give like this: IC is equal to Vs root C by L sine omega t. And when this current is flowing through any capacitor, the voltage changes its value by the expression of Vc is equal to Vs 1 minus cos omega t. How we are going to get this expression? Because we know Vc is equal to 1 by C integration I dt. So when we put this value of I in that expression, we will get capacitor voltage expression by this: Vc is equal to Vs 1 minus cos omega t. And this charging current will continue in this circuit till the voltage across capacitor is not changing its value from plus Vs to minus Vs. That means by the end of this mode, the capacitor lower plate will be positive and upper plate will be negative. So if I talk about at the end of mode 1, capacitor voltage changes its value from plus Vs to minus Vs, and in mode 1 it is changing by the expression of Vs 1 minus cos omega t, means it will change its value from plus Vs to minus Vs cosinusoidally. At the end of mode 1, the capacitor voltage will be minus Vs with lower plate positive and upper plate negative. The second point about the mode 1, that in this mode the charging current changes by the expression of Vs C by L sine omega t, and at the end of mode 1, once the voltage across the capacitor is minus Vs, the charging current will be 0. And as you can see in mode 1, the both charging current and the load current both are flowing through T1 in the similar direction. So your current flowing through thyristor T1 will be I0 plus IC. So that means you can see that the current flowing through thyristor T1 will be I0 plus IC. That you can see here, it is I0 plus IC. I0 is Vs by Z and IC is equal to Vs root C by L sine omega t. And your current through diode, as the IC is passing through diode, so the current through diode will be equal to IC. Now in mode 2, which exists from T1 to T2, if I see at the end of mode 1, which is the beginning of mode 2, the capacitor is charged with a reverse voltage of lower plate positive, upper plate negative. Due to this capacitor voltage, you can see now this capacitor voltage through T1 short circuit is appearing to diode as a reverse bias, so it will be off. And although this capacitor voltage through T1 is making the TA forward bias, but again it will be off because we have not given any triggering pulse to TA. As in this mode 2, as the D is off, TA is off, so only one path of flow of current is there, that is through plus Vs, T1 load and minus Vs. So in this case, the load current will be only one current will flow, which is from plus Vs, T1 load and minus Vs, and the value of that current will be the load current, and that is equal to Vs by Z. In this case, there is no charging current is there because the TA is open, D is open, so there is no possibility to the flow of current through capacitor. So charging current will be 0. And since there is no charging current is flowing through capacitor, so there is no question of change of voltage. So whatever the voltage will be there at the end of mode 1, that was Vs, that will remain at minus Vs. There is no change in the Vc. In this case, as the diode is open, so ID is 0, and there is only one current flow through thyristor T1, that is equal to I0. And what is I0? That is equal to Vs by Z. In this mode, only one device is conducting, that is T1. So this is something about the mode 2. Now let us talk about mode 3. So mode 3 exists from T2 to T3, and at the beginning of mode 3, as in the mode 2 itself, the TA was forward biased due to this capacitor voltage, but it was not conducting as the firing pulse is not given to it. But what we do in the beginning of mode 3, we give the triggering pulse to TA also. So as we give the triggering pulse to TA, so it will be short circuit. Now due to this short circuit, this capacitor voltage is now appearing to T1, and this capacitor voltage through T1 short circuit is appearing to T1 as a reverse bias voltage. And we know there is a property of a capacitor that voltage across capacitor cannot change abruptly. That means this capacitor voltage through this TA short circuit is able to appear across T1 in a reverse bias condition for a sufficient duration. Because of that, T1 is off. So this will be the equivalent circuit in the mode 3. Now in this case also there is only one path of flow of current which I have shown by red line, and this is nothing but it's a load current, and as this load current is passing through capacitor also, so this is a charging current also. In this mode only TA is conducting, T1 is off and D is also off. Only one current which I have already mentioned, that I0 is equal to IC. I0 will be in this mode, it will be constant. And what is this value? What is the magnitude of this I0? The magnitude of this I0 will be Vs by Z. And what is this current? So load current in this case is constant, that is Vs by Z. Now you can see here, as this Vs by Z load current, as we know, let me show it in the next slide. What is I0? I0 is Vs by Z. And in mode 3, I0 is equal to IC also. So what is IC? Vs by Z. So what is voltage across capacitor? That is 1 by C integration IC dt. So when I put this value Vs by Z dt, so what capacitor voltage I am getting? Vs by Z into C into T. So that means in this mode, as the charging current is constant, so voltage across capacitor is changes its value linearly with a slope of Vs by Zc, because this Vs by Zc into T is the equation for a straight line. So it will change its value linearly. So this is what I want to tell you. So that means in mode 3, the voltage across capacitor changes its value linearly. So at last, I can conclude capacitor voltage changes linearly from minus Vs to plus Vs by the expression of Vs by Zc into T. The capacitor current or the charging current in this case is Vs by Z, which I already mentioned. And at the end of this mode 3, capacitor is charged by a reverse voltage. That means upper plate is positive and lower plate is negative, which makes TA reverse bias and make it off, as well as T1 is forward bias. That means at the end of mode 3, we are again reached to the same situation as at the beginning of mode 1. So now, and as the situation of the circuit is exactly similar as the beginning of mode 1, so let me draw so that it will be clear to you. So what is the situation at the end of mode 3? The capacitor upper plate positive, lower plate negative. This is T1, this is TA, this is D, this is L, this is L, and here it is load, here plus minus Vs, and this is RC. Now, as due to this capacitor voltage and the supply, T1 is forward bias. So as soon as we give the triggering pulse to T1, so it will be short circuit, and this D will also be short circuit. So this is the situation as the situation of the circuit at the beginning of mode 1. So that means after mode 3, the situation in the circuit is exactly same as was at the beginning of mode 1. So again the process can start in the same fashion, Now let us draw the waveforms. let me take the graph. So let us, this is IG1, that is the firing pulse to thyristor 1. This is firing pulse to thyristor A. This is load current. This is charging current. This is thyristor 1 current. This is ID. This is VC. And this is VT. Suppose up to this point, so this is 0, this is T1, this is T2, and this is T3. This is mode 1, this is mode 2, and this is mode 3. Now IG1, as you know that we have given the triggering pulse at t is equal to 0 itself. So this is the waveform for IG1. Now you know that at the beginning of mode 3 we have given the triggering pulse to TA, so that is 6. We have assumed that load current is constant as well as continuous, so load current will be parallel to x-axis and that is equal to I0 and this is equal to Vs by Z. Now let me draw IC. What is IC? IC we know Vs root C by L sine omega t. In mode 1 it is varying like this, so that is sinusoidal variation, and mode 2 mein it was 0 and mode 3 mein it was constant. You can see that in mode 1 mein the charging current is going from downward to upward. Mode 2 mein charging current is 0, but when you see mode 3 the charging current is coming from upward to downward. So that means if in mode 1 if I have plotted like this, so mode 2 mein it will be constant is equal to I0 and it is constant, that is equal to I0, and this peak will be Vs root C by L. So this is the charging current. Now if I plot IT1, what is IT1? In mode 1 IT1 will be I0 plus IC. So that means it will be shifted. Your sinusoidal waveform will be uplifted by, this is Vs by Z up to this, and this is sinusoid, this is I0 and this is IC, and IT1 in mode 1 that is the addition of I0 plus IC. So that means the sinusoidal waveform uplifted by Vs by Z, and after that the IT1 was equal to I0, that means Vs by Z, and later on in mode 3 it was 0. So this is your IT1. Now what is ID? ID is equal to IC in mode 1 and mode 2 mein it is 0, mode 3 mein it is 0. What is VC? VC changes its value from plus Vs to minus Vs coincidentally. Mode 2 mein it will sustain at plus Vs to minus Vs. Mode 2 mein it will sustain at minus Vs, and mode 3 mein it will be changes its value from minus Vs to plus Vs but linearly. Okay. Now what is VT1? Mode 1 mein VT1 is conducting, so short circuit. Mode 2 mein also it is conducting, so short circuit. Mode 3 mein, if you see mode 3, at every time the way the capacitor voltage changes, in a similar way through TA short circuit is appearing to T1. So why the T1 is off in mode 3? Because this capacitor voltage was appearing to T1 as a reverse bias. So that means in mode 3 the capacitor voltage changes its value from minus Vs to plus Vs but linearly, because as the capacitor voltage changes, the voltage across the T1 is also changing in a similar fashion. So it will also changes its value linearly. So these are the waveforms. I have plotted IG1, that is the firing pulse to T1, IGA firing pulse to auxiliary thyristor, I0 which we have assumed constant and continuous, IC in mode 1 it is Vs root C by L sin omega t and the peak value is Vs under root C by L. Mode 2 mein the charging current is 0 and mode 3 mein it is equal to load current and that is equal to Vs by Z. So it is constant but in negative direction. IT1 in mode 1, it is the addition of I0 plus IC. So that means the sinusoidal waveform uplifted by I0, that is Vs by Z, and then mode 2 में Vs by Z, and mode 3 में it is 0. IT in mode 1 it is equal to charging current, and rest of the mode it will be 0. Vc changes its value from plus Vs to minus Vs cosinusoidally, then it will sustain at minus Vs, and then linearly changes its value from plus Vs to minus Vs. Why linearly? Because the charging current in mode 3 is constant. And similarly, we have plotted for G1. So now I am stop sharing my screen. I hope whatever information I have shared in this video related to the class D commutation, I started with the power circuit diagram, and then I discussed about its various operating modes, discussed about what will happen in the mode 1, what will happen in mode 2 and 3. Then at last I draw the waveforms also. So I hope now it is clear why it is called as a voltage commutation also, because in the explanation you have seen, then the first we are building the voltage across a capacitor in a reverse direction in the mode 1, and then that reverse voltage by giving the firing pulse to the thyristor TA at the beginning of mode 3, we are appearing that capacitor voltage to the main SCR in a reverse bias condition. So because of the voltage commutation, the main SCR is off. So that's why it is called the voltage commutation. Now my dear friends, I hope whatever information I have shared in this video, that will be useful for you. If you like this video, kindly press the like button, and if you feel that whenever I make such kind of videos related to the power electronics, the notification should reach to you, then don't forget to subscribe my channel. Thank you.